Okay, welcome to Panhandle Skies video podcast number 2. My name is Steve Douglas. I'm a storm spotter with the Amarillo Emergency Service here in town, and I'm also a storm photographer. And this podcast is going to be a lesson on storm structure. That way, when you go out storm spotting or trying to photograph your own storms, you have a better idea what you're looking at. This is not intended to be a advanced storm spotters class, nor to take place of one. So if you do go out, you should attend a certified National Weather Service storm spotter class. So we'll start out here now with a photograph I took last year of a typical LP supercell storm. This one was in Carson County, and it was a dry line storm, which meant it grew in advance of a area of dry air colliding with a area of moist air coming up from the Gulf over Carson County. So while this storm did not have a lot of rain in it, it did have a lot of hail, and it did produce a tornado. This one is a textbook example of an LP storm. We'll start out first by showing you the wind patterns. We have moist air coming in from the southeast into the storm. This is the fuel for the storm. Dew points on this side of the storm are probably in the 50s or 60s. And then on the other side of the storm we have dry air coming in. This is the dry line. Maybe it might be a dry cold front. It might just be an area of dry. It might even dry warm front for that matter. And where the two collide is where we have our storm, and we get uplift. And we get uplift, we get storm towers. So these two air masses are coming and colliding right here, and because they're colliding, they are drawn upward, especially the moist air coming in from the Gulf, and it builds these storm towers that you see here. These towers will build and build and build until they hit the jet stream up here. Well, it'll flatten out and it gives us that classic anvil shape. Sometimes in some storms the updraft is so strong that it'll actually go above the jet stream and cause what's called a cap or an overshooting top. We'll look at that in just a little bit. This is the updraft area. This is the downdraft area over here where the hail and the rain will be, but since this is an LP storm, there's not a lot of rain and hail to obscure any of the features. The most likely part of the storm where a tornado would form would be in this area right here. You also notice that we have a lot of lean in this storm. This isn't a straight up and down storm. This is a storm that's got some tilt into it. And when you have tilt, it's pretty indicative of winds moving in opposite directions at different levels. So we have air coming into the storm from this direction, going that direction, and then we have moisture coming in from the other direction, going this direction. And when you have that, you have a tendency to get rotation in a storm. In between these two levels of winds, you'll actually get some rolling going on, just like if you took a pencil between your fingers and rolled it on a desk. So you'll get a rolling motion, and that's kind of, you can see that kind of in the way these clouds have kind of a rolling round shape to them. And all we have to do is tilt this rolling action to the vertical, and we get a tornado. On to our next photo. This is a classic illustration of what's called an overshooting top or a cap cloud. We have the jet stream, which is rushing along here. And then we have a terrific updraft. These are updraft towers here. They're actually so potent that they're going above the jet stream. This is pretty indicative of a very severe storm. A storm that has a overshooting top like that, you can count on hail. You can count on high winds. Here's something that meteorologists have noticed, that when these overshooting tops fall, when they collapse on themselves and they send air rushing down back behind the storm towards the ground, you get something called the RFD, or the rear flanking downdraft. The rear flanking downdraft is a key component in tornado formation. It can actually help get a tornado started. So if you see one of these overshooting tops collapse, you'll know probably within 20 to 30 minutes you could have a tornado in that storm. Now, unfortunately, you have to be about 20 miles away from a storm to be able to see this part of the cell, so you wouldn't be close enough to see the tornado form. But if you're doing some nowcasting and you have somebody inside the storm and somebody away from the storm watching the top of the storm, and they do see an overshooting top collapse, they should radio the spotter and let them know, because when this happened, tornado formation could be imminent. Okay, this last photograph in our podcast is of a stovepipe tornado I shot in Carson County last year. This is a great photograph to illustrate what happens at the bottom of a storm and the winds that cause a tornado to form. Let me show you some of these features here, highlight them for you so you'll be able to recognize it when you go out into the field. One of the most important features is this light area here, which we call the clear notch. It's caused by the RFD, the rear flanking downdraft that we were talking about earlier, when that cap cloud at the top of the storm collapsed and sent all the air rushing back down behind the storm. And as the air rushed down, it dries out, and it sends wind down at the back edge of the storm. And because it's dry, it develops this clear notch. You do not want to be underneath this RFD, because the winds coming down could be in excess of 80, 90, 100 miles an hour and can flatten structures. Meteorologists theorize that it is a key component in tornado formation, because some of these winds, when they hit the ground, they spread out and they actually wrap around the updraft and actually impart some more rotation and spin in the storm, causing tornado formation, especially if you already have rotation in higher levels of the storm and you don't have it in low levels. This RFD can actually help spin the storm. There's some other structures I want to point out to you too. Of course, this is the wall cloud here. This would be the entire part of the upward flow of the storm, the updraft part of the storm. All the winds will be rushing up into the storm here, feeding the storm. Dry air will be coming in from this direction. Moist air will be coming in from this direction here, feeding into the storm. You'll notice you can actually see striations in this storm, what we call barber poling, which shows you, it's not only indicative of a rotation in the storm, but also shows you divergent winds. You have winds wrapping around each other, going in different directions, causing rotation and shear, which of course causes tornadoes. One more feature I wanted to point out to you is what we call the beaver tail, and that's that area here. You can see it kind of sloping into the storm, and basically what it is an inflow jet of moist air feeding the updraft. This is an intense inflow jet, and it will help fuel rotation in the storm. So when you have these features together, the dry slot, the RFD, these areas of winds begin to mix, and then they begin to rotate, and soon, quite possibly, you have a tornado. So that's our first basic lesson in storm spotting, and I hope you enjoyed it. And when you go out there, I hope you look for these features and be safe.